Right now, as you watch this, you're hurtling through space at 67,000 miles per hour. You don't feel it, you can't sense it, but it's happening. And that's not even the strangest part. The light hitting your eyes right now left distant stars before Earth existed. Ancient photons, traveling at 670 million miles per hour for billions of years, just to reach you in this exact moment. You think you understand what big means. You think you grasp the scale of our world. You're about to discover how catastrophically wrong you are. We're going to journey past objects so dense that a spoonful would weigh more than Mount Everest. We'll witness explosions that release more energy in 1 second than our sun will produce in its entire lifetime. We'll encounter structures so vast that light, the fastest thing in existence, needs millions of years just to cross them. And here's what will really break your brain. By the end of this journey, everything you consider enormous will seem smaller than an atom. Your city, your country, your entire planet will become cosmically invisible. But we're getting ahead of ourselves. First, we need to destroy something fundamental: your perception of Earth's size, the lie you've been living. You believe Earth is huge. Of course you do. It takes hours to fly across it, days to sail around it. You've built your entire sense of scale around this planet. Walking to the store is a journey. Driving across your state consumes hours. Flying to another continent eats up a full day. These experiences feel significant because you experience them one step at a time. Every mile reinforces the illusion that Earth is vast. Every trip convinces you that our planet is something substantial. Here's the truth that will shatter that illusion. In the cosmic scale, Earth is smaller than a dust particle in a cathedral. No, that's not dramatic enough. Earth is smaller than a single bacterium on a dust particle in a cathedral the size of a continent. Still don't believe me? Let's prove it. The moon looks small enough to cover with your thumb, right? It's actually 240,000 miles away. You could stack 10 Earths end to end between here and there and still not bridge that gap. 10 entire planets, and you're still just reaching our nearest neighbor. And here's what makes this genuinely disturbing. Your brain physically cannot process these numbers. Evolution never equipped you to comprehend distances measured in millions or billions. Your survival-focused mind was designed to track prey across valleys, not calculate astronomical distances. When you hear a million or a billion, your brain treats them identically. Both just mean really big number. But the difference is staggering. A million seconds is 11 days. You could experience that. A billion seconds? 32 years. You'd age from childhood to middle age. The difference isn't just large, it's generational. It's the span of an entire human life. Now, scale that up. If you shrank our entire solar system down to the size of a city block, Earth would vanish. You couldn't see it with your naked eye. And our solar system, that invisible speck of a city block, is just one point among 400 billion stars in our galaxy. We haven't even left our cosmic neighborhood yet, and already the numbers are becoming impossible to grasp. The crushing prison you can't feel. Right now, an invisible ocean is crushing you with the weight of an elephant. Every square inch of your body is being pressed down with 14.7 pounds of force. You've never noticed because you've lived underwater your entire life, underwater in an ocean of air. This atmospheric blanket that keeps you alive? It only extends a few dozen miles up before it gives way to the void. Space officially begins at 62 miles up. Sounds close, doesn't it? Here's what that actually means. If you stacked 60,000 people on top of each other, you'd barely reach the edge of space. Imagine that tower of humans stretching up and up and up, beyond where clouds form, beyond where jets fly, beyond where weather exists, into the black. Most jets cruise at 6 to 7 miles high. At that altitude, without pressurization, you would die in 15 seconds. Not slowly, not peacefully. Your blood would literally boil as the air pressure dropped too low to keep it liquid. You're still less than 10% of the way to space. Mount Everest, that mountain that kills experienced climbers regularly, peaks at 5.5 miles. You'd need to stack 11 Everests on top of each other to reach space. Want the truly disturbing perspective? Shrink Earth to basketball size. The atmosphere becomes thinner than a sheet of paper wrapped around it. Every breath you've ever taken, every storm that's ever raged, every cloud that's ever floated, all of it exists in a layer so thin it might as well not be there. 5 quadrillion tons of air pressing down on you, and yet compressed to water density. It would form an ocean only 34 feet deep. All that weight, all that pressure, represents a coating of gas so negligible that on cosmic scales, it's essentially invisible. We live at the bottom of an impossibly thin ocean of air, clinging to a rock hurtling through space, and we think we're stable. We think we're safe. We're wrong. The closest we've ever gone. The International Space Station orbits at 250 miles up. Astronauts float not because gravity disappeared. Earth's pull there is still 89% as strong as on the surface. They float because they're falling. Constantly. Forever. They plummet around Earth at 17,500 miles per hour, while the planet's curve drops away beneath them at exactly the same rate. Here's where it gets strange. The space station orbits closer to Earth's surface than the distance between New York and Washington, D.C. That's a 3-hour drive. You could literally drive to the space station faster than you could drive to a neighboring city. This pathetic distance, this tiny hop away from Earth's surface, represents the absolute pinnacle of human space achievement. In all of history, fewer than 600 people have traveled even this far. 600. Out of billions who have lived and died. Our species' greatest journey? The moon. 3 days away by rocket. And we're still trapped in Earth's gravitational prison. We haven't escaped. We haven't even really left. The numbers are already becoming unwieldy. And we've barely moved. But compared to what's coming, the space station might as well be touching the ground. The star that owns us. Sunlight warming your face is 8 minutes and 20 seconds old. Those photons traveled 93 million miles through empty space to reach you. But here's what should make you uncomfortable. In that same time span, light could circle Earth's equator 7 times. This reveals something you haven't considered about the sun's true size. Light, the universe's absolute speed limit. The fastest thing possible needs over 4 seconds just to cross the sun's diameter. It laps our entire planet in 1/7 of a second, but needs 4 full seconds to cross our star. The sun could contain 1 million Earths, not side by side, completely inside its volume. 1 million planets our size, swallowed whole, and there'd still be room left over. It holds 99.86% of our solar system's mass. Jupiter, Saturn, all the planets, all the moons, all the asteroids, all the comets combined, they represent 0.14%. If the solar system were a pizza, the sun would be everything except a few microscopic crumbs at the edges. The sun's surface reaches 10,000 degrees Fahrenheit, hot enough to vaporize anything. Steel turns to gas, diamond becomes vapor, but that's actually the coolest part we can observe. Deep in the core, temperatures hit 27 million degrees. There, hydrogen nuclei collide with such violence they fuse into helium, releasing the energy that makes life possible. Every second, the sun annihilates 4 million tons of matter, converting it directly to pure energy. 4 million tons, every single second. This has continued for 4.5 billion years and will persist for 5 billion more. 1 second of solar output could power our entire civilization for hundreds of thousands of years. And despite this awesome, terrifying power, the sun is classified as average, a yellow dwarf, unremarkable. Our galaxy contains stars that make the sun look like a dying ember next to a supernova. Consider this final disturbing fact. The sun sits 93 million miles away, appearing as a small disk you can cover with your pinky finger. Yet staring at it directly will permanently destroy your vision in seconds. This average, ordinary star completely governs our planet's fate. Without it, Earth would freeze solid within days. The oceans would ice over. The atmosphere would snow out as frozen nitrogen. Everything would die. We are utterly, completely, helplessly dependent on this ball of nuclear fire 93 million miles away. But against what's approaching, the sun is barely a candle in the cosmic darkness. Pluto sits in eternal darkness at what most people think is the edge of our solar system. Temperatures never rise above -375 degrees Fahrenheit. The sun appears as just another bright star, providing barely more warmth than distant starlight. This frozen world orbits 3.7 billion miles from the sun so far that light takes over 5 hours to reach it. But here's what destroys your sense of scale. Pluto isn't even close to the true edge. Beyond Pluto lies the Kuiper Belt, a ring of icy objects extending another billion miles outward. Thousands of frozen worlds, remnants from our solar system's birth, orbit in perpetual darkness. And beyond that, the Oort cloud, a spherical shell of comets reaching 50,000 times farther from the sun than Earth. 50,000 times. That distance is so vast it makes the journey to Pluto look like walking to your mailbox. If you could shrink our entire solar system down to a grain of sand, the nearest star would still be over a mile away. Picture holding a grain of sand, then walking more than a mile to find the next one. That's the space between stars. That's the emptiness we live in. Voyager 1, launched in 1977, has been screaming away from the sun at 38,000 miles per hour for nearly 5 decades. It has barely left our solar system. It won't approach another star for 40,000 years. Even at light speed, it would take over 4 years to reach our nearest stellar neighbor. The space between stars contains almost nothing. In the emptiest regions, you might find 1 hydrogen atom per cubic foot. Earth's atmosphere contains trillions upon trillions in the same space. Interstellar space is more empty than the best vacuum we can create in laboratories. This emptiness extends in every direction for distances that would consume lifetimes to cross at light speed. And this is just our local neighborhood. The galaxy that devours. But compared to what comes next, our stellar neighborhood is just getting started. Our galaxy is eating other galaxies right now. This very second, the Milky Way is slowly devouring smaller galactic groups, stretching them into streams of stars that wrap around us like cosmic spaghetti. This cannibalism has continued for billions of years. We're mapping the stellar graveyards as we speak. The Milky Way contains between 200 and 400 billion stars, each one potentially hosting its own family of planets. Some might harbor life. Some might harbor civilizations looking up at their night sky, wondering if they're alone, just like we do. If you counted 1 star per second, non-stop, never sleeping, it would take you over 12,000 years to count them all. That's longer than recorded human history, but the number of stars isn't what should terrify you. It's the distance between them. Our galaxy measures 100,000 light-years from edge to edge. Light needs 100,000 years to cross it. Voyager 1 would need 1.7 billion years to make the same journey. By the time Voyager crossed our galaxy, if it could somehow survive that long, the sun would have burned out completely. Earth would be gone, consumed or ejected. The galaxy itself would have merged with neighbors and changed shape entirely. Any civilization that launched Voyager would be extinct, their ruins ground to dust, their existence forgotten. But here's what makes galactic distances truly incomprehensible. We're not sitting still. Our entire solar system orbits the galactic center at 515,000 miles per hour. At this insane speed, it still takes 230 million years to complete one orbit. Dinosaurs lived and died during our last quarter orbit. When our solar system was last in this position, T-Rex walked the Earth. The Atlantic Ocean was narrower. The continents were shaped differently. The galactic center hides a supermassive black hole containing 4 million suns crushed into a region smaller than Mercury's orbit. Stars near the center orbit this monster so fast, they complete full circuits in just 16 years, despite traveling at thousands of miles per second. Time itself runs slower for them due to extreme gravity. Einstein predicted this. We've now observed it. From our position, 26,000 light-years from the center, we cannot see the core due to dust clouds. But if you could remove the dust, the galactic center would glow in our night sky as bright as the full moon. Billions of ancient stars packed so densely they'd create perpetual daylight. We live in the suburbs, far from the dangerous downtown. Most of our galaxy's stars will never be explored. They're simply too far away. Our entire galaxy, 400 billion stars, countless planets, unimaginable distances, is just one island in an infinite ocean. And we haven't even begun to comprehend what's out there. The real journey starts now. A star named Jwst is so monumentally large that if you placed it where our Sun currently sits, it would engulf Mercury, Venus, Earth, and Mars completely. Its outer edge would extend past Jupiter's orbit. Light would need 9 hours to travel around this monster's circumference, 9 hours at 670 million miles per hour. If you could somehow drive around Jwst's equator at highway speeds, the journey would consume 9 million years. You'd need to start driving when our ancestors were still primitive apes and continue driving until today, and you still wouldn't be halfway around. Jwst belongs to a class of stars called red supergiants. These stellar behemoths represent the final phase of the most massive stars' lives. When a star contains more than 25 times our Sun's mass, it burns through its nuclear fuel at an incredible rate. The more massive the star, the shorter and more spectacular its existence becomes. While our Sun will burn steadily for 10 billion years, Jwst will exist for only about 10 million years total. It burns hydrogen fuel so rapidly that it's already in its death throes. Despite being relatively young in cosmic terms, the star's outer layers have expanded to tremendous size as the core struggles to maintain nuclear fusion against its own crushing gravity. Here's what makes Jwst truly mind-bending. Despite being 1.7 billion times larger than our Sun in volume, it only contains about 30 times more mass. This means the star is incredibly diffuse. Its outer atmosphere is so thin that it's essentially a vacuum by Earth's standards. If you could somehow stand on a platform within Jwst's outer layers, you might not even realize you were inside a star. The gas around you would be thinner than Earth's atmosphere at high altitude. You'd see a faint glow, but you could look around and see through the star's outer layers to space beyond. Only deeper down, closer to the core, does the density and temperature rise to stellar levels. But Jwst isn't even close to being the most massive star we know. That title belongs to stars in the R136 cluster, located 165,000 light-years away in a neighboring dwarf galaxy. These monsters contain up to 300 times our Sun's mass, packed into much smaller volumes. They burn so hot and bright that they blast their outer layers into space with stellar winds moving at thousands of miles per second. These winds are so powerful they strip away the star's own mass. The star essentially evaporates itself through sheer radiation pressure. It's like a cosmic blowtorch pointed outward in all directions, shedding millions of tons of material every year. The most massive stars we can observe push against theoretical limits for stellar formation. Above a certain mass threshold, a star becomes so hot that radiation pressure prevents it from accumulating more material. Light itself pushes away infalling matter. These stellar giants burn through their fuel so quickly that they exist for only a few million years before exploding catastrophically. When Jwst finally dies, it will likely explode as a supernova visible during daytime on Earth, despite being thousands of light-years away. The explosion will outshine our entire galaxy for several weeks. The blast will forge and scatter elements heavier than iron throughout space, seeding future generations of stars and planets with the raw materials necessary for complex chemistry and life. But compared to what comes next, even these stellar monsters are surprisingly delicate structures. A neutron star designated PSR J17482446 AD rotates 716 times per second. In the time it takes you to blink once, this stellar corpse completes over 200 full rotations. Its equator moves at nearly 100 million miles per hour, roughly 15% the speed of light. Any faster and centrifugal force would tear the star apart, flinging pieces of it into space like a cosmic grenade. Neutron stars represent what happens when a massive star's core collapses under its own gravity during a supernova explosion. In less than 1 second, a region the size of Earth gets crushed down to a sphere just 12 miles across. The collapse is so violent that protons and electrons get smashed together to form neutrons, hence the name. What remains is the densest matter in the known universe. A neutron star contains more mass than our Sun compressed into a volume smaller than Manhattan. Picture cramming more than 300,000 Earths into an area you could walk across in a few hours. The gravitational field at its surface is 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star's surface, you would instantly weigh the same as Mount Everest. Every atom in your body would be crushed flat. You wouldn't fall to the surface, you'd impact it with the force of a nuclear bomb. The escape velocity from a neutron star is 100,000 miles per second, nearly half the speed of light. But the density is what truly shatters comprehension. 1 teaspoon of neutron star material would weigh 6 billion tons on Earth. That's more than all the cars, trucks, and buses on the planet combined, compressed into something you could hold in your hand if your hand could somehow support it, which it absolutely couldn't. A sugar cube of this material would weigh as much as a mountain. If you somehow transported it to Earth's surface, it would plunge through the ground, through bedrock, through the mantle, all the way to the planet's core, its immense gravity pulling it toward the center like an unstoppable bullet. The magnetic field around a neutron star is 1 trillion times stronger than Earth's magnetic field. To put that in perspective, a neutron star's magnetism from 100,000 miles away is strong enough to erase every credit card on Earth. It would scramble the atoms in your body, disrupting the chemical bonds that hold you together. This intense magnetism funnels charged particles along the magnetic poles, creating beams of radiation that sweep through space like lighthouse beams. When these beams point toward Earth, we detect regular pulses of radio waves. That's why we call them pulsars, pulsating stars. Some neutron stars are even more extreme. Magnetars have magnetic fields 1,000 times stronger than regular neutron stars. These fields are so intense, they warp the quantum vacuum itself, creating electron-positron pairs from empty space. The magnetic field energy of a magnetar could power human civilization at current consumption rates for 1 billion years. If a magnetar erupted within 50 light-years of Earth, its burst of X-rays and gamma rays could strip away our ozone layer and trigger mass extinctions. The radiation would sterilize one side of our planet. Fortunately, no magnetars exist that close to us. Neutron stars are incredibly long-lived. While massive stars burn out in millions of years, neutron stars can spin for billions of years with atomic precision. The most stable pulsars keep time more accurately than the best atomic clocks humans have built. Astronomers use pulsar timing to detect gravitational waves and navigate spacecraft across the solar system. When 2 neutron stars spiral into each other and collide, they create kilonova explosions that forge gold, platinum, and uranium. Every gold ring, every platinum catalyst, every uranium atom on Earth was created inside these cosmic collisions billions of years ago, before our sun even existed. But compared to what comes next, neutron stars seem almost normal. When neutron stars collide, drop a marshmallow onto a neutron star, and it would impact the surface with the explosive force of 1,000 hydrogen bombs. NASA calculated this scenario to demonstrate the ridiculous gravitational field surrounding these stellar remnants. The marshmallow would accelerate to millions of miles per hour in the fraction of a second it takes to fall to the surface. The surface of a neutron star is the smoothest place in the universe. Any mountain on a neutron star would be limited to about 1/10 of an inch in height before the intense gravity crushed it flat. The surface exists in a state somewhere between solid and liquid, crystallized under pressures we can barely imagine. The surface gravity is so strong that it warps space and time visibly. Light climbing out of a neutron star's gravity well loses energy, becoming redder and dimmer by the time it reaches Earth. This gravitational redshift is predicted by Einstein's general relativity and confirmed by observations. Neutron star surfaces experience starquakes that make Earth's most powerful earthquakes seem like gentle tremors. When the neutron star's crust shifts by just a fraction of an inch due to changes in the interior, it releases more energy than Earth's sun produces in 100,000 years. These starquakes can change the star's rotation rate in milliseconds, causing pulsar glitches that astronomers can detect from thousands of light years away. But the real violence happens when matter falls onto a neutron star from a companion star. In binary systems, a neutron star can slowly strip gas from a normal star's outer layers. This stolen gas spirals inward, forming an accretion disk that heats to millions of degrees. When enough material accumulates on the surface, nuclear fusion ignites in a thermonuclear explosion that can be seen from across the galaxy. These X-ray bursts release more energy in seconds than our sun produces in weeks. The explosion is so energetic it briefly doubles the system's brightness. Some neutron stars strip matter from companion stars so efficiently that they become recycled pulsars. The infalling matter spins up the neutron star like a cosmic gyroscope, causing it to rotate hundreds of times per second. These millisecond pulsars are among the most precise timekeepers in the universe, maintaining their rotation rates to within nanoseconds over decades. The magnetic fields around neutron stars create phenomena that have no equivalent anywhere else in the universe. Near the magnetic poles, electrons accelerate to nearly light speed, creating beams of gamma rays so intense they could kill every living thing on Earth from 1,000 light-years away. When these death beams sweep across space, they create the lighthouse effect that allows us to detect pulsars. But if one pointed directly at Earth continuously, rather than sweeping past, the radiation would be catastrophic. Neutron stars also demonstrate Einstein's general relativity in ways impossible to study anywhere else. Time runs measurably slower in their intense gravitational fields. Light gets bent around them, allowing us to see parts of their backside by looking at their front. Their rotation drags space and time around with them in an effect called frame. Dragging the spinning star literally pulls the fabric of space-time along with it. But compared to what comes next, even neutron stars follow predictable physical laws. Cosmic cannibalism. Binary neutron star systems are cosmic vampires that slowly devour each other over millions of years. When two neutron stars orbit close together, they create gravitational waves, ripples in space-time itself that carry energy away from the system. This energy loss causes the stars to spiral closer and closer together in a deadly dance that can only end in collision. The most famous binary neutron star system, called the Hulse-Taylor binary, provided the first indirect proof of gravitational waves decades before LIGO detected them directly. The two neutron stars in this system orbit each other every 7.75 hours. Each orbit, they lose energy to gravitational waves and move 17 feet closer together. In about 300 million years, they will collide in a spectacular explosion. But some neutron stars don't wait for collision to steal from their neighbors. When a neutron star has a normal companion star, it can pull material from the companion's outer layers through gravitational force. This stolen gas forms a glowing accretion disk that spirals into the neutron star at millions of miles per hour. The friction in this disk heats the gas to temperatures exceeding 100 million degrees Fahrenheit. These accreting neutron stars become X-ray sources so bright they outshine entire galaxies. The infalling matter releases gravitational energy more efficiently than nuclear fusion ever could. When gas finally hits the neutron star's surface after spiraling inward, it's moving at thousands of miles per second and carries kinetic energy equivalent to nuclear weapons detonating continuously. The impact creates X-ray bursts that can temporarily increase the system's brightness by factors of millions. Some binary systems create even stranger phenomena. Black widow pulsars are neutron stars that slowly evaporate their companion stars with intense radiation. The pulsar's energetic particles strip away the companion's outer layers like wind eroding a cliff, creating a glowing cloud of gas around the system. Eventually, over millions of years, the companion star will be completely consumed, leaving behind an isolated pulsar surrounded by a debris disk, the graveyard of its former partner. Redback pulsars represent another class of cosmic cannibals. These are neutron stars with companion stars massive enough to survive the pulsar's radiation assault, but still small enough to lose material to their dense partner. The interaction creates complex patterns of X-ray emission as material flows between the stars in an intricate gravitational ballet. The most violent binary interactions occur when two neutron stars finally merge after millions of years of spiraling together. The collision creates a kilonova explosion that synthesizes heavy elements and ejects them into space at thousands of miles per second. These mergers are responsible for creating most of the gold, platinum, and rare earth elements in the universe. The collision crushes neutrons together under such extreme conditions that they build up heavy nuclei through rapid neutron capture. This process can only occur in the most extreme environments, and neutron-star mergers are the most extreme environments that exist. But compared to what comes next, stellar cannibalism is just an appetizer for cosmic violence on a grander scale. On the 17th of August 2017, gravitational wave detectors felt space itself vibrate as two neutron stars collided 130 million light-years away. The merger, designated GW170817, lasted just 100 seconds, but released more energy than our Sun will produce in its entire 10 billion-year lifetime. The collision created an explosion called a kilonova that was visible to amateur astronomers on Earth, despite occurring in a galaxy far beyond our own. For several days, this single event outshone all the stars in its host galaxy combined. The night sky briefly contained one more star that hadn't been there before the death cry of two neutron stars merging into one. But the light show was just a byproduct of something far more significant happening at the subatomic level. When two neutron stars merge, they create conditions that exist nowhere else in the universe. Temperatures reach 100 billion degrees hotter than the Big Bang was 1 second after it occurred. Densities exceed that of atomic nuclei. Neutrons get crammed together so tightly that they form elements heavier than iron through rapid neutron capture. This process creates gold, platinum, uranium, and dozens of other heavy elements in just seconds. The collision ejected roughly 50 Earth masses of pure heavy elements into space at thousands of miles per second. Think about that. 50 times Earth's mass in gold, platinum, and rare elements, thrown into space by a collision lasting less than 2 minutes. This single event created more gold than exists in Earth's entire crust. The platinum in your jewelry, the gold in your electronics, the uranium powering nuclear reactors, all of it was forged in stellar collisions like this one, billions of years ago, before our Sun existed, before our solar system formed. But neutron-star mergers don't just create elements. They also provide crucial tests of fundamental physics. The collision generated gravitational waves that traveled across 130 million light-years without losing their information content. These waves confirmed Einstein's predictions about how space and time behave under the most extreme conditions. The merger also produced a short gamma-ray burst, one of the most energetic explosions in the universe. For just 2 seconds, this burst released more energy in gamma rays than our Sun produces in visible light over millions of years. If a similar burst occurred within a few thousand light-years of Earth and pointed in our direction, it could strip away our ozone layer and cause mass extinctions. The radiation would sterilize whatever hemisphere faced the burst. Fortunately, these events are rare and the beams are narrow. Scientists estimate that neutron-star mergers occur roughly once per year in a galaxy the size of the Milky Way. Over cosmic time, these collisions have enriched the universe with heavy elements necessary for rocky planets and complex chemistry. Without neutron-star mergers, the universe would contain only hydrogen, helium, and lithium, the elements created in the Big Bang. There would be no carbon, no oxygen, no silicon for rocks, no iron for planetary cores. No heavy elements means no rocky planets. No rocky planets means no life as we know it. The gravitational waves from GW170817 also provided a new way to measure the expansion rate of the universe. By combining gravitational wave data with optical observations of the kilonova, astronomers calculated the Hubble constant, the rate at which the universe is expanding with unprecedented precision. But compared to what comes next, neutron-star collisions are just the beginning of cosmic mysteries that challenge everything we thought we understood about matter and energy. Dark matter outweighs all the stars, planets, gas, and dust in the universe by a ratio of 5-to-1. Every atom in your body, every grain of sand on Earth, every star in the night sky, all of it represents just 16% of all matter that exists. The other 84% is completely invisible and interacts with ordinary matter only through gravity. We know dark matter exists because we can see its gravitational effects on everything else. Galaxies rotate too fast to hold together based on visible matter alone. Stars at the edges of spiral galaxies should be flung into intergalactic space by their orbital speeds, yet they remain bound. Galaxy clusters move in ways that require 5 times more mass than we can observe. Gravitational lensing bends light around massive objects in patterns that demand invisible matter. But here's what makes dark matter so profoundly mysterious. It passes through ordinary matter as if nothing exists. Right now, billions of dark matter particles are streaming through your body every second without interacting with a single atom. They pass through Earth like it's not even there. Dark matter particles might be colliding inside you constantly, but they leave no trace of their passage. Scientists have built detectors deep underground, shielded by miles of rock, hoping to catch dark matter particles in the act of occasionally bumping into normal atoms. These experiments require isolation from cosmic rays and radioactive contamination because dark matter interactions are so incredibly rare and weak. After decades of searching with increasingly sensitive equipment, we still haven't directly detected a single dark matter particle. We can see what it does, how it affects galaxies, how it bends light, how it holds galaxy clusters together, but we cannot catch it or identify what it actually is. The leading theory suggests dark matter consists of particles called WIMPs, weakly interacting massive particles. These hypothetical particles were created in the first moments after the Big Bang, but have completely different properties from ordinary matter. They don't emit light, don't absorb light, and don't interact electromagnetically at all. They're invisible, intangible ghosts that outnumber normal atoms 5-to-1. Alternative theories propose that dark matter might be primordial black holes formed in the early universe, or axions, or sterile neutrinos, or something even stranger that we haven't imagined yet. Some scientists question whether dark matter exists at all, suggesting instead that our understanding of gravity needs modification on cosmic scales. What we do know is that dark matter played a crucial role in structure formation. In the early universe, dark matter began clumping together first because it didn't interact with radiation. These dark matter clumps provided gravitational scaffolding that allowed ordinary matter to collect and form the first stars and galaxies. Without dark matter, the universe would look completely different. Galaxies wouldn't exist. Stars wouldn't have formed when they did. The cosmic web of structure we observe today required dark matter's invisible hand to shape it. Computer simulations show that dark matter forms a cosmic web of filaments and nodes throughout the universe. Galaxies form where ordinary matter falls into dark matter halos, vast invisible structures that dwarf the galaxies themselves. The Milky Way sits inside a dark matter halo extending far beyond the visible galaxy's edge. But compared to what comes next, dark matter is just the supporting framework for an even stranger cosmic component, the dark matter prison. The Milky Way is trapped inside a spherical prison made of dark matter that extends 3 times farther than our galaxy's visible edge. This invisible halo contains 10 times more mass than all the stars, gas, and dust we can observe. Without this dark matter cage, our galaxy would have flown apart billions of years ago. Our galaxy rotates like a cosmic pinwheel, but the rotation doesn't follow the rules of normal physics. Based on the visible matter alone, outer stars should orbit much slower than inner stars, just like planets in our solar system. Neptune orbits slower than Mercury because it's farther from the Sun's gravity. Instead, stars throughout the galaxy's disk all orbit at roughly the same speed of about 500,000 miles per hour. This flat rotation curve was one of the first major pieces of evidence for dark matter. Astronomer Vera Rubin discovered in the 1,970 seconds that galaxy after galaxy showed the same impossible rotation pattern. The only explanation was invisible matter providing additional gravitational pull to keep the outer stars moving so fast. She measured galaxy after galaxy, and they all showed the same thing: rotation curves that made no sense unless most of the galaxy's mass was invisible. Dark matter halos extend much farther than the galaxies they contain. The Milky Way's dark matter halo reaches out roughly 300,000 light-years from the galactic center. For comparison, the visible galaxy is only 100,000 light-years across. We live inside this vast, invisible structure that shapes everything about our cosmic environment. The dark matter halo isn't smooth or uniform. Computer simulations reveal that it contains substructure, smaller dark matter clumps left over from the formation process. Some of these dark matter subhalos might contain their own small galaxies, dim dwarf galaxies orbiting in the Milky Way's outer reaches. Others are completely dark, invisible except for their gravitational effects. As the Milky Way moves through space, it's constantly collecting dark matter from its surroundings. The galaxy acts like a cosmic vacuum cleaner, pulling in dark matter particles and smaller dark matter clumps. This process has been happening for over 13 billion years, gradually building up our galaxy's invisible mass. The local group of galaxies, which includes the Milky Way and Andromeda, exists within an even larger dark matter structure spanning millions of light-years. This structure contains the mass equivalent of 10,000 trillion suns, most of it in dark matter we cannot see. Dark matter also influences star formation within our galaxy. The gravitational pull from dark matter clumps can trigger the collapse of gas clouds, leading to bursts of star formation. The distribution of dark matter throughout the galaxy affects where and when new stars are born. In about 4 billion years, the Milky Way will collide with the Andromeda galaxy. But the dark matter halos will collide first, their invisible masses interacting gravitationally long before the visible galaxies meet. Larger dark matter structure that will contain the merged galaxy. But compared to what comes next, dark matter is a passive player in an even more dramatic cosmic story. The phantom energy. Dark energy is ripping the universe apart at an accelerating rate. This mysterious force makes up 68% of everything that exists, yet we have no idea what it actually is. Dark energy acts like anti-gravity, pushing space itself to expand faster and faster over time. 5 billion years ago, dark energy overcame gravity and began accelerating the expansion of the universe. Before this cosmic transition, gravity was winning the battle, slowing down the expansion left over from the Big Bang. Now, dark energy dominates, and the expansion rate increases every day. The universe will expand forever, growing colder and emptier with each passing billion years. This is the ultimate fate of our cosmos, an endless expansion into darkness. On small scales, dark energy has no effect. Gravity easily overpowers dark energy within galaxies, star systems, and planetary systems. Your body, Earth, and even our entire galaxy are gravitationally bound strongly enough to resist dark energy's expansion. The atoms in your body aren't being pulled apart. The solar system isn't expanding. But on larger scales, dark energy rules everything. Galaxy clusters represent the largest structures that gravity can hold together against dark energy. Clusters containing thousands of galaxies span tens of millions of light-years and contain the mass of millions of billions of suns. Even these massive structures are now being stretched apart by accelerating expansion. The local group, containing the Milky Way and Andromeda galaxies, will remain gravitationally bound forever. In about 4 billion years, these two galaxies will merge into one giant elliptical galaxy. eventually nicknamed Milkomeda by astronomers. But most other galaxies are already moving away from us faster than we could ever reach them, even traveling at light speed. Currently, we can observe galaxies up to about 46 billion light-years away. But dark energy ensures that this cosmic horizon will eventually shrink, in a sense. Galaxies at the edge of our observable universe are moving away from us faster than light speed, not through space, but because space itself is expanding between us and them. Eventually, even nearby galaxy groups will disappear beyond our cosmic horizon. In trillions of years, any observers in the merged Milkomeda galaxy will look out and see nothing. No other galaxies, no distant stars, just the stars within their own galaxy surrounded by infinite darkness. In the far future, dark energy will create a lonely universe. Each gravitationally bound galaxy group will become isolated in its own expanding bubble of space. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe will approach maximum entropy, the heat, death, where no energy gradients exist and nothing can happen anymore. Dark energy will continue pushing empty space apart until the universe becomes a cold, dark void containing nothing but the faint whispers of evaporating black holes and the random motion of fundamental particles scattered across infinite distances. Scientists have proposed several theories for dark energy's nature. It might be vacuum energy, quantum fluctuations in empty space that create a constant outward pressure. It might be a dynamic field called quintessence that changes strength over time. Some theories suggest dark energy strength might change, leading to even more dramatic cosmic evolution, possibly even a big rip, where dark energy becomes so strong it tears apart galaxies, then stars, then planets, then atoms themselves. But we simply don't know. Dark energy is one of the deepest mysteries in physics. We've measured its effects with precision. We know it makes up more than 2/3 of the universe, but we don't understand what it is or why it exists. But compared to what comes next, dark energy is just setting the stage for cosmic objects that challenge everything we thought we knew about physics. A supermassive black hole called 3C273 blazes with the light of 4 trillion suns. Despite being smaller than our solar system, this monster sits at the heart of a distant galaxy, consuming stars and gas at such a furious rate that it outshines every star in its galaxy combined. The energy it releases in 1 second equals what our sun produces in 10 million years. Quasars represent supermassive black holes in their most violent feeding phase. When galaxies collide or merge, enormous amounts of gas get funneled into the central black hole. This material forms a superheated accretion disk that glows brighter than anything else in the universe. The disk reaches temperatures of billions of degrees, hot enough to strip electrons from atoms and create a plasma more energetic than the core of any star. This isn't normal fire or even nuclear fusion. This is matter being torn apart and accelerated to near light speed by gravity alone, releasing its energy as it spirals toward oblivion. But here's what makes quasars truly mind-breaking. They achieve this incredible luminosity through pure gravitational energy. As matter spirals into a black hole, gravity accelerates it to nearly light speed. The conversion of gravitational potential energy to heat and light is far more efficient than nuclear fusion. While stars convert less than 1% of their mass to energy through fusion, black holes can convert over 30% through accretion. This means black holes are the most efficient engines in the universe for converting mass to energy. Nothing beats them. The most luminous quasar we've discovered, designated J529-4000-351, shines with the brightness equivalent to roughly 500 trillion suns. This single object, powered by a black hole containing billions of solar masses, releases more energy every second than hundreds of billions of stars combined. It's so bright that we can see it from over 12 billion light-years away. The light we detect today left that quasar when the universe was less than 2 billion years old. Quasars also launch jets of material at 99.9% the speed of light. These jets extend for millions of light-years beyond the host galaxy, creating radio emissions detectable across cosmic distances. The magnetic fields channeling these jets are stronger than anything we can create on Earth, yet they maintain their focus across distances larger than galaxy clusters. The jets carry enormous energy. In some cases, they contain more energy than all the stars in the host galaxy. They blast through intergalactic space, creating giant radio lobes that dwarf entire galaxies. When these jets collide with intergalactic gas, they heat it to millions of degrees and create shockwaves that ripple across vast distances. Most quasars existed when the universe was young and galaxies were smaller, closer together, and more likely to interact. In the early universe, galaxy mergers happened frequently, providing abundant fuel for supermassive black holes. Today's universe is more spread out, so quasars are much rarer. The Milky Way's central black hole is currently starving, consuming less material than a typical asteroid every year. It's quiet, dormant, barely accreting anything. But 4 billion years from now, when we collide with Andromeda, the merger might funnel gas into our central black hole and briefly reignite it as a quasar. When a quasar finally exhausts its fuel supply, it fades to become an ordinary galaxy with a dormant supermassive black hole at its center. Every large galaxy we observe today likely went through a quasar phase billions of years ago. The supermassive black hole in our galaxy's center represents what's left after our own quasar era ended. But compared to what comes next, even these cosmic lighthouses are just nearby neighbors in a universe far stranger than we imagined. The nearest known quasar sits 2.5 billion light-years away from Earth. Even traveling at light speed, the journey would take 2.5 billion years. But the universe is only 13.8 billion years old. You could have started when the first stars formed and still wouldn't be halfway there. When we observe this quasar, we're seeing it as it existed 2.5 billion years ago, when Earth had only primitive single-celled life. The light we detect left before animals existed, before plants colonized land. But most quasars lie much farther. The most distant one, J313-1806, existed when the universe was only 670 million years old. Its light has traveled for over 13 billion years. Here's what makes this staggering. Space itself expanded while the light traveled. When that quasar emitted the light we see today, it was closer, maybe only a few billion light-years away. Cosmic expansion carried it away during the light's journey. Today, that same quasar is over 46 billion light-years distant. At such distances, we're not just looking into space, we're looking back in time. Astronomy becomes archaeology. Every quasar observation captures cosmic conditions billions of years in the past. The light also gets stretched by expansion. This redshift makes ultraviolet radiation become infrared by the time we detect it. Some quasar light has been pulled like taffy across billions of years. These ancient quasars pose a mystery. How did supermassive black holes containing billions of solar masses form so quickly? They shouldn't exist yet, but there they are. Fully formed monsters when the universe was still young. But compared to what comes next, these beacons are just streetlights in a cosmic city we're beginning to map. Quasar light traveling across cosmic distances passes through gas clouds that leave absorption fingerprints in the spectrum. These create what's called the Lyman alpha forest, a series of absorption lines that look like vertical bars in the spectrum. Each line represents a hydrogen cloud between us and the quasar. By studying thousands of quasar spectra, astronomers map how matter was distributed when the universe was young. These maps reveal the cosmic web in unprecedented detail. When quasar light passes near massive objects, gravitational lensing bends it and creates multiple images of the same quasar. Some appear as perfect Einstein rings, when alignment is exact light bent into circles by gravity. The most powerful quasars ionize hydrogen across hundreds of millions of light years. During the early universe, quasars helped reionize all the neutral hydrogen, determining how galaxies could form. Blazars are quasars with jets pointing directly at Earth. They can vary in brightness by factors of hundreds in just days. When a blazar flares, it temporarily becomes the brightest object in the gamma-ray sky. But compared to what comes next, Even these cosmic beacons are individual points in a web spanning everything. The local group of galaxies spans 10 million light-years and contains over 80 galaxies, yet it occupies less than 1% of the space inside a typical cosmic void. Cosmic voids are the largest structures in the universe, regions where dark energy pushed matter apart so effectively that galaxies become rare. The Boötes void spans 330 million light-years and contains almost no galaxies. If the Milky Way sat in this void's center, we wouldn't have discovered other galaxies until the 1990 seconds. Our understanding of cosmic history would have been delayed by a century, but voids aren't completely empty. They contain sparse gas filaments and occasional dwarf galaxies. These void galaxies tend to be smaller, bluer, and more actively forming stars than galaxies in dense regions. Void boundaries are defined by sheets and filaments of galaxies forming the cosmic web. Galaxy clusters form where filaments intersect. Our local group sits within a filament connecting the Virgo cluster to the Fornax cluster, part of the Laniakea supercluster spanning 520 million light-years. The cosmic web emerged from tiny density fluctuations in the early universe. Dark matter clumped first, then ordinary matter fell into those gravitational wells, forming the first stars along cosmic filaments. The web has hierarchical structure. Smaller filaments connect to larger ones, which connect to even larger sheets and walls. The largest walls extend over 1 billion light-years. The distribution follows patterns similar to soap bubbles or neural networks. Large voids surrounded by thin walls of matter, with dense nodes where walls meet. But compared to what comes next, even these voids are just gaps in highways carrying galaxies across the cosmos. Cosmic filaments stretch hundreds of millions of light-years, forming the universe's largest structural elements. The filament containing our local group extends over 500 million light-years. Yet it's one strand in a network spanning everything observable. Individual filaments contain the mass of 10 trillion suns stretched across distances light needs hundreds of millions of years to cross. Despite enormous size, they're surprisingly thin, typically only a few million light-years wide. More extreme than human hair compared to its length. Filaments are crucial because they're highways along which galaxies travel and grow. Matter flows from low-density regions toward high-density nodes where clusters form. This cosmic traffic system has operated for over 13 billion years. The Pisces-Cetus supercluster complex spans over 1 billion light-years, containing thousands of galaxy groups in a roughly linear pattern. Recent observations detected filament gas directly for the first time. X-ray telescopes found million-degree plasma between clusters, confirming predictions. This plasma contains more than half of all ordinary matter in the universe, hidden in near vacuum between galaxies. This solved the missing baryon problem. Most ordinary matter predicted by Big Bang nucleosynthesis was unaccounted for. It exists in these hot filaments, too diffuse for optical telescopes but detectable in X-rays. Filaments also channel dark matter flows at thousands of kilometers per second. When flows converge at intersections, they create the most massive galaxy clusters. Filament formation began in the first few 100 million years after the Big Bang. The patterns preserve information from when the universe was less than 1% its current age. But compared to what comes next, even these highways are infrastructure supporting the largest objects that exist. The Hercules Corona Borealis Great Wall stretches 10 billion light-years across space, the largest known structure in the observable universe. This cosmic wall contains billions of galaxies arranged in a sheet that would take light 10 billion years to cross. But here's what breaks your brain. The Great Wall is so large it challenges our understanding of structure formation. Theoretical models predict structures this massive shouldn't exist. There hasn't been enough time since the Big Bang for gravity to assemble them. The Great Wall consists of gamma-ray bursts and galaxy clusters, arranged in patterns persisting across billions of light-years. These bursts mark massive star deaths, tracing the underlying matter distribution. Other megastructures include the Sloan Great Wall at 1.37 billion light-years and the South Pole Wall at 1.4 billion light-years. Each discovery pushes boundaries of what we thought possible. These structures also challenge the cosmological principle, the assumption that the universe looks the same in all directions on large scales. Structures spanning significant fractions of the observable universe question this fundamental assumption. But compared to what comes next, even these record-breaking structures are just patterns within something far stranger. If the universe is finite and curved back on itself, we might be observing the same galaxies multiple times without realizing it. Light from a single galaxy could travel around the universe's curvature and reach us from different directions, the same object at different ages. The cosmic microwave background suggests the universe is either infinite or at least 250 times larger than what we can observe. A finite universe would create a cosmic hall of mirrors. Every object would produce multiple images scattered across the sky, each showing different evolutionary stages. A galaxy might appear young and blue in one direction, while simultaneously appearing old and red in another. Detecting these duplicates requires sophisticated statistical analysis. Some studies claim evidence for cosmic duplication, but others dispute these findings as random fluctuations. Different topologies would create different patterns. A universe wrapped like a three-dimensional torus produces one pattern. A spherical universe creates another. The topology determines how many duplicate images exist and where they appear. But compared to what comes next, cosmic topology is just one puzzle piece in understanding the true boundary of everything observable. The edge of everything. The cosmic microwave background represents the farthest edge ancient light marking when atoms first formed and the universe became transparent. This radiation has traveled 13.8 billion years, carrying information from when the universe was only 380,000 years old and 1,100 times smaller. Before this moment, the universe was opaque. Free electrons scattered photons so efficiently that light couldn't travel. We can never observe anything before this with electromagnetic radiation. The cosmic microwave background provides a baby picture of the universe when it was smooth and nearly uniform. Tiny temperature variations, just millionths of a degree, represent seeds that grew into galaxies, stars, and planets. The surface where this radiation originated now lies 46 billion light-years away due to cosmic expansion. Those atoms have since been incorporated into billions of star generations. Some hydrogen that created this background might now exist in your body. This ancient radiation fills the universe uniformly. Every cubic inch of space contains about 400 cosmic microwave background photons. Cosmic expansion redshifted them from visible light to microwave frequencies. What once blazed at stellar intensity now appears as faint glow at 2.7 degrees above absolute zero. The background's near-perfect uniformity creates the horizon problem regions that should never have contacted appear identical in temperature. Cosmic inflation solves this by proposing all observable space was once smaller than a subatomic particle. Precision measurements determined fundamental cosmic parameters with unprecedented accuracy. We know the universe's age, density, composition, and geometry from studying these ancient photons. But this ultimate boundary only illuminates the observable portion of a universe extending far beyond our horizon. The observable universe is just a tiny bubble within a cosmos, potentially extending infinitely. We only see light that's had time to reach us since the Big Bang, creating a boundary 46 billion light-years away. Beyond lies more universe, potentially infinite, forever hidden. Cosmic inflation suggests the entire universe is vastly larger than the observable part. During the first fraction of a second, space expanded exponentially, stretching a region smaller than a proton to grapefruit size in less than a trillionth of a trillionth of a trillionth of a second. Conservative estimates suggest the universe is at least 10 to the 23rd power times larger than the observable portion. If the observable universe were a light bulb, the actual universe would be larger than the Milky Way. An infinite universe would contain infinite copies of everything. Every possible matter arrangement would occur infinitely across infinite space. Infinite versions of you reading these words right now. Eternal inflation proposes our observable universe is one bubble in an infinite multiverse. Inflation never completely stopped, but continues creating new space eternally. Our Big Bang represents one local event where inflation ended. Each inflation bubble would have its own physics determined by how fundamental fields settled. Some bubbles might have stronger gravity, others weaker electromagnetic forces. Most might be unsuitable for any structure or life. The inflationary epoch solved multiple cosmology problems simultaneously: why the universe is flat, uniform, yet contains structure seeds. It took a tiny connected region and stretched it to cosmic scales. Current observations support inflation through the flatness, uniformity, and structure of our observable universe. The cosmic microwave background shows exactly the fluctuation pattern predicted: nearly scale-invariant density perturbations from quantum fluctuations. If inflation is correct, the answer to how big is the universe is stunning. Either impossibly larger than observable or literally infinite. Either way, everything we see, every star, galaxy, cosmic structure, represents less than nothing compared to reality's true scale. The universe began smaller than a period at the end of a sentence, then grew to become larger than we can comprehend, and it might still be growing, creating new space, new possibilities, new realities beyond imagination. This is the true scale of existence, a cosmos so vast our entire observable universe becomes insignificant. We are incomprehensibly, impossibly, magnificently